Good morning, ladies and gentlemen. This is the May 22nd, 2019 briefing session of the Utah Board of Oil, Gas, and Mining. We'll start with you, Director Baza. Good morning. And we want to say thank you to all those that were involved in the Environmental Excellence Awards from last evening. That was a really good event with great food and a lot of preparation and a lot of work setting it up and taking it down, and it was very appreciated. Mr. Baza.
Thank you, Mr. Chairman, and members of the board. Welcome to your May hearing in Salt Lake City. I'm John Baza, the director for the division, and to add to what the chairman said about the Environmental Excellence Awards, I'd like to give shout outs to two individuals, Julianne Carter, the board secretary, who helped with a lot of the arrangements, but especially to Holly Brown, our public information officer, who coordinates the Environmental Excellence Awards from start to finish. She was a big help and important part of making sure those awards came off as well as they did last night. So thank you so much, and thank you to the members of the board who were present for those. It is my pleasure to start out today's briefing with a introduction of somebody I've known for about 23 years, Dr. John McLennan, and I'm going to read you some information from his background. Since October of 2009, Dr. McLennan has been an associate professor in the Department of Chemical Engineering at the University of Utah. He's been a senior research scientist at the Energy and Geoscience Institute and a research professor in the Department of Chemical Engineering at the U since January of 2008. He has a PhD in civil engineering from the University of Toronto in 1980. He has 30 years of experience in geomechanics with petroleum service and technology companies. Oops, I skipped the line.
That's okay.
But I would say that I met John when he worked for TerraTech in Salt Lake City. He's also worked for Advantech International in Houston and ASRC Energy Services in Anchorage. And at the request of a couple of board members who were at our hydrocarbon conference in Duchesne in April, where Dr. McLennan presented, they asked that we have a special session to have him back this morning and specifically present information to the board on the geologic potential of the Uinta Basin. So without further ado, I'll turn the time over to Dr. McLennan.
Thank you, John. Good morning to the board. I'm really pleased to be here this morning. Many of my colleagues in the room are surprised that we have an engineer giving a talk on geology, but in the interest of time, we'll keep the geologic side relatively brief, and we'll go into some of the up-and-coming engineering issues that I think we're seeing with movement towards horizontal drilling, if that's okay. The credit for the geologic side on this talk goes exclusively to Mike Vandenberg, and if indeed you need briefing on the geology of the Uinta Basin, Mike happens to be the world's expert in terms of that, and I'm building on a presentation that he gave last December. And so I don't think I need to describe the contents of this particular slide, where we're dealing with oil and gas fields in the Uinta Basin. Mostly Green River formation, with also the Wasatch and the Flagstaff. Now historically, we've had largely vertical or directionally near vertical wells, and more recently we're seeing horizontal wells being drilled. And I think one of the interesting things that we're seeing is the implications of these horizontal drillings and some of the precautions that may need to be taken even from a regulatory perspective. I'm not qualified to comment on regulatory or policy, but I think that there are issues that will come up. These wells typically tend to be in lacustrine deposits, lake-oriented deposits with fluvial and deltaic sands or carbonates, and they're often accompanied by water flooding and tertiary recovery. The gas fields, as we know, are Cretaceous to Eocene in the Wasatch and the Mesa Verde And so we can look sort of at a simplified geologic schematic where we'll start at the Mancos, the Cretaceous Mancos. You know, Mancos is a very thick formation that's been touted for 40 years plus, and may one day be a source of additional gas and possibly in some parts of the basin oil we're actually seeing. Above that, we have the Mesa Verde, then we have the Wasatch, Flagstaff, and we can move upwards, and we'll just walk through those formations briefly so that we can keep this in line. I think I can skip this slide because I know this audience is very familiar with the prolific nature of production from the Uinta Basin. So the Uinta Basin owes its credentials and heritage to ancient Lake Uinta. And what we can see here is we can see three lakes forming on the trilateral joining of Utah, Colorado, and Wyoming. And the particular formations that exist are a function, to a large extent, of transgressions and regressions, fluctuations in the size of ancient Lake Uinta. As the lake becomes smaller, you typically have more sand-rich deposits from erosion. Climatic control controls the level of water in the lake, and as the level of water in the lake becomes greater, you typically have deeper water deposits with finer grained materials and the occurrence of shales and carbonates that occurs. As the lake recedes in parts of the basin, you'll see more coarse-grained deposits, higher porosity, higher permeability deposits that are sometimes premium for our oil and gas discovery, and those are associated with deltaic and fluvial origins. So this ancient Lake Uinta, we can go back, say, to the Flagstaff limestone, maybe at the start of the Eocene. 50-odd million years ago is the start of the Eocene, 56, I guess. And Lake Flagstaff covered the western Uinta Basin and the Wasatch Plateau. And this was a freshwater lake, and as a consequence of that, the fauna that occurred in there were freshwater. There was a lot of mollusks, and there are interbedded siliciclastic intervals. So siliciclastic just implies that it's silica-oriented. Clastic implies largely an erosional origin. And there can be tongues of higher permeability sands that form within the lower permeability materials, and those are often preeminent deposits for production. We can move upwards to the Wasatch and the Colton formations, and as you can see from this figure, the size of the lake has become considerably smaller than ancient Lake Flagstaff. And as a consequence of that, we're seeing fluvial deposits, maybe higher permeability material, higher porosity materials, but there are still muds, lower permeability materials that are present. And a lot of geologists stay up at night worrying about the origin of water that filled Lake Uinta. And it is a relevant question because of paleoclimates and understanding climates at some time in the past. We can move further up to the formation that has really been getting a lot of attention in the last decade. And this tends to be the Uteland Butte Formation. It's a member of the Green River Formation. And as you can see, it's associated with the transgression, meaning an increase in the size of ancient Lake Uinta. And with that transgression, we had different facies present, geologic depositional environments forming a facies. And in those facies, we have bivalves and gastropods, just different kinds of wildlife that formed. These are dominantly carbonate formations, and we're particularly interested in the dolomitic formations that exist. Subsequent to that, and naturally occurring above this because of the geologic history, there was a regression of Lake Uinta, and once again we have fluvial sands forming, we have muds, and we have riverbeds, red beds, iron-rich formations near shore, and once again there's a potential for production in some of these areas that we're seeing in formations that are known as the Wasatch, the Colton Tongue, or the Castle Peak. The bottom line is that those formations really offer a tremendous resource to Utah, a lot of it unexploited, and there remain opportunities. The greater and even larger scale opportunity, but commercial viability may escape us even for some time in the future, are the oil shales associated with the Mahogany Formation, deposited about 50 million years ago. This is when Lake Uinta was at its highest elevation. It was a stratified lake. Organic matter was preserved, and the reason for preservation typically is it's an anoxic environment where oxygen wasn't present and materials, hydrocarbon materials were preserved. But as we all know, oil shale is not oil and it's not shale. It's typically carbonate material, and it's typically kerogen, which has to be pyrolyzed or processed in some fashion before it's a usable fuel product. So where does this all go? What you can see is there's been a rich history of drilling in the Uinta Basin, and rich opportunities still exist. So the question I ask is of these wells in the Uinta Basin, well, how many of these wells are horizontal? Well, recognizing, wells being drilled since Ashley Valley and whatever, many of those wells are vertical. And in fact, when this talk was put together, the count was about 285 of these 17,000 wells were horizontal. And so we're just sort of catching on to the wave of horizontal wells, and it's really made a difference in terms of some of the production. You can look at the production centered around these wells and you can draw some conclusions. And here's where the conclusions become kind of important to understanding exploitation of the basin in the future. These wells are decent. You can see wells that are producing 2,500 barrels a day, and those are nationally and internationally competitive wells. But what you'll notice a couple of boundaries that are drawn on here. And one is the extent of the Uteland Butte. That's not necessarily a showstopper because there are other formations other than the Uteland Butte, but many people have derived significant production by exploiting the Uteland Butte. The second line that is even more important, we'll talk about this a little further, is the line of overpressure. And overpressure typically occurs in a basin during geologic time where the rate of deposition of sediments is so rapid that it is not possible to dissipate the pore pressure that is accumulated hydrostatically. So what you end up with is you end up with pore pressures that are in excess of the hydrostatic pressure. And typically what people have found in modern reservoirs and even historic reservoirs, particularly modern reservoirs where the permeability may be low, is that favorable production is often associated with pressures that are greater than hydrostatic, overpressured reservoirs, so greater than half a psi per foot. So if I just had a column of water, it would be, of pure water, it would be 0.433 psi per foot. And so what we can see is this boundary of half a psi per foot is pressures that are existing in the formation that are higher than the hydrostatic pressure of water. And that higher pressure, you can imagine the value of it because the higher pressure is part of the gradient in pressure that drives fluid into a well. You have higher pressure out here, you have lower pressure in your well, and the greater that difference, the greater that drive acts towards production. And so we can see that favorable production has been grouped into this overpressured zone. And it is spread out into formations other than the Uteland Butte. It's in Uteland Butte, the Castle Peak. There are some boutique production, and I don't mean boutique, from a geologic perspective boutique because of the G1 limestone, but favorable production. And we can see that there are opportunities other than the Uteland Butte. The Castle Peak is a little different from the Uteland Butte. It's sandier, okay, siliciclastic, so silica-based sand, clastic erosional deposition, higher porosities, higher permeabilities, and so opportunities that people are exploiting in that particular formation. We can also see formation in the lower part of the Green River with the Wasatch, with the Wasatch and the Flagstaff. And you can notice the number of horizontal wells that are shown on this plot, either single section or double section horizontal wells. And as with everything else, we found these days that to a large extent, the length of these horizontal wells and the magnitude of the stimulation that's put on these wells is correlative with the production that we often see in these wells. We can just sort of skip through this. So if we can just focus in on, and I realize I'm doing this very quickly, but I mean, this information is available. The engineering aspects are probably more critical for us to deal with immediately because I think the resource is there and it's the exploitation and extraction that is going to be relevant. Within the Uteland Butte, we're looking at a couple of dolomites bounded between two shales, and often we'll find that the spacing between those two shales, the C shale and the D shale, as you can see on this figure, once again offers some correlation to the production that exists. So if we look at how things stand now, we can see Uteland Butte production, once again, bounded by the extent of the Uteland Butte Formation and characterized by the magnitude of the in situ formation pressure that is there. And so the message that we take out of this is that there really are some opportunities that remain in these overpressured regions. We can be looking at lithologies other than Castle Peak. And one of the things that we need to worry about, and I'll come back and I'll talk about this a little further, is the ability to optimize spacings and treatments that exist in these particular wells to overcome parent-child conflicts. And parent-child conflict is a pretty good metaphor for what actually happens in these wells. So the basis is that you drill one particular well, and you stimulate and you produce that well. With the reduction in pressure that's associated with the stimulation that exists in this well, there is a reduction in the in situ stresses. Okay, so there's a poroelastic, what's known as poroelastic coupling between the magnitude of the stresses and the magnitude of the pore pressure. So as I reduce my pore pressure, there's a tendency for the in situ stresses in that particular area to go downwards. And hydraulic fractures are governed by the magnitude of the in situ stress field that exists. So if you have a producing parent and the stress field is reduced because of that production, and I put in an infill well and I fracture, there tends to be an attraction between the fracture in the infill well and the reduced stress domain in the parent well. And what that means is that there's an inefficient fracturing that occurs in the child well, and production in the child well may not be as large as anticipated. Beyond this, there's the concept of frac hits, and we'll talk about that briefly too. That with this reduction in stresses, fractures from the child are attracted towards the parent, and there's a strong chance of intersection of previous fractures and direct communication with the wellbore and inefficient fracturing in the first place. So in other parts of the country, this has become really a major, major issue where there's a lot of concern that goes on. I sort of diverged there. I got off topic, but I think we'll come back to it. So one of the things that we see in these overpressured wells is that there are some possibilities for dealing with this. And before we deal with this, we need to understand what causes it. And so the causes are related to the reduction in stress that are associated with the production that occurs in these wells. And so in the overpressured region, we have some things that can be done to encourage equal production from parents and child and minimize interaction between these wells. In the underpressured region, this is where the prize may really exist in terms of resource, because we have resource in the underpressured regions outside of this magical 0.5 psi per foot contour. But we have to think about methods for production that become economic. And to a certain extent, we may need to be looking at application of tertiary recovery techniques earlier on, earlier water flooding, injection of gas. Those are some of the things that people are exploring in other parts of the country. We may be looking at accelerated flowback. What that means is that you do a stimulation on a well and you produce back the fracturing fluid faster so that it's not imbibed into the formation. Because the lower the pressure, the harder it is to get that fracturing fluid back out after you've done a stimulation. So there's a lot of engineering things that can be done in the overpressured region and the underpressured region. And one of the greatest things is understanding the interaction between wells. And ultimately, this may be something that's on the table of regulators and policymakers. Here is something that's taken from the annual presentation of Diamondback. Diamondback is an operator in the Permian Basin. And in the lower figure, you can see they pointed out styles of drilling wells in different formations that they're dealing with in the Midland Basin. So on the Midland Basin on the left-hand panel and the Delaware Basin on the right-hand panel. And what you can see is that you can see that we're moving away from restricted number of wells per section. So each one of those vertical lines there is indicating a section boundary in a particular formation. And so, for example, if we go to the bottom left, and Fang turns out to be who Diamondback is, you can see that in the middle Sprayberry, they're putting 6 wells in a section. In the lower Sprayberry, they're tightening the wells up, et cetera, et cetera. And you can see that some operators, in fact, are using a wine rack or a stacked chevron configuration for putting wells in place. Well, what's governing sort of some of the issues and the frequency of these wells is interaction between these wells and the spacing that exists in those wells. And so I might want to point people to kind of an obscure journal. I have a copy with it, of the article that's in there, but it just recently came out and it's talking about when do fracture interactions really occur. And this is such a huge industry problem that it's really dominating journals and publications a lot. And so we can see fracture interaction even before we've started to frack an offset well. We can see it during diagnostic fracture injection testing, defit injection testing, where we can see active injection into one well and we can see a pressure signature in another well. So you can imagine that as you're injecting, you're putting fluid into the formation, you're creating a fracture, and basically you're compressing the formation between these 2 wells. So even without transfer of fluid, you can sense pressure in the passive well. During fracture stages, you can see interactions. So you have multiple stages of fractures going on, and the fractures that we create in a single well are not as simple as we commonly think. We deal with concepts that are called stress shadowing, where the presence of one fracture inhibits the propagation of another fracture, even during the same fracturing stages. And then certainly after fracturing, we can see interference and sharing of production because wells move together. So let's just look at a couple of examples here to explain this from the point of view of geomechanics. So the example on the right, let's imagine that across the bottom on the x-axis here, we have a horizontal well, and we have a simplified situation where we have 2 clusters within a stage that we're fracturing. If we have a case, as in the left, where the minimum horizontal stress is much less than the maximum horizontal stress, these fractures are going to grow and not interact. Well, why is that? Well, what controls the propagation of a hydraulic fracturing is that a hydraulic fracture opens up perpendicular to the smallest in situ stress. Okay, and so there's a small in situ stress, and it turns out that at 90 degrees to that, there's the largest stress. So the greater the difference between the smallest and the largest stresses, the more organized these fractures are going to be, and you'll have a situation at left. If we have a situation, as exists in certain basins, that the stresses are approximately equal, here the minimum is about 98% of the maximum, you have these fractures interacting. And as a matter of fact, these 2 fractures are acting to oppose each other and move off in different directions. It becomes even more complicated if you're starting to deal with multiple clusters. Okay, so you have a stage where you have 5 perforation clusters, well, more than that in this case, I guess 6 in this case. And the interaction, you're pumping down and fluid is trying to go to all these clusters equally. The fluid doesn't make it to all the clusters equally. Some fractures dominate. Some clusters take more fluids than others, and fractures become longer. Those longer fractures tend to inhibit the growth of the shorter fractures, and vice versa. The fact that you only have single fractures occurring or dominant fractures, those fractures can be longer, and they can interact with fractures with wells that are farther away. So sometimes our fractures are longer than we'll see from fracture simulations. Often it becomes even more complicated, particularly in situations where the stresses are lower, and you can get a case where the stresses that are caused by one large fracture can turn out to attract a secondary fracture. And very, very complicated networks. Not necessarily bad for production, but just complex to predict. So people have talked about this concept of fracture shadowing, and this figure kind of illustrates it. This is in a single well. And fracture shadowing in a single well, what you're saying is that one fracture stage that you've done early is affecting the performance of a fracture that you're doing later on. So imagine you do a fracture early on. You're propping open that formation. You're locking in stresses in that formation. And then I do a fracture later on. The stresses are higher because I've locked in stresses from this earlier fracture. So you see this even in single wells, where the blue line here shows for individual fracture stages, as time is going on, that the pressure required to inject into these wells becomes higher and higher, moving on into these wells. And there's a whole host of mechanical and treatment parameters that are causing this, ranging from, you can imagine, the closer the stages are together, the closer the clusters are together, the more interaction you're going to have. If you have poor hydraulic connection, isolation along the wellbore, you can grow fractures along the wellbore. So there are many, many things that contribute to these frac-to-frac connections here between wells. So that's talking about single wells, where you can have fracture interaction in single wells. Suppose, as we go back to this parent-child relationship, you can have interaction between wells, interactions, where you can have fracture. The fracture from one well intersects a fracture from another well, and that's a pathway into that well. And there have been many reported cases where those communications have been established, where you've actually been putting fracturing fluid and proppant in the passive well and basically destroying that well in some cases, losing pipe, failing casing, and whatever. So I'm just going to run through a number of cases to show that this is a serious problem, and this is something where these interactions happen over surprisingly large distances. So here's one example from Bomber et al. In North Dakota, in the Basin and the Sanish formations. And there were wells in the Three Forks Sanish, and there were wells in the Basin. And these were open hole wells. They had liners in them. Between open hole liners, they had open hole packers, and you would frack between the packers. And the first well was fracked 11 months before the second well. Long-term communication was immediately established, and these wells horizontally were 1,300 feet apart, and a vertical separation between these two formations of more than 100 feet. So substantial distances, substantially larger distances than we might commonly predict using conventional fracture modeling. Here's another one from the Marcellus Formation in the northeastern part of the country. Okay, these wells were 500 feet and 1,000 feet apart, and tracer was pumped in these wells. So basically, during a frac stage, somebody was pumping a liquid tracer, and that tracer was sensed by fluorimetry or some other technique at this monitoring well. And those wells were 500 feet apart. And in another case, they reported 1,300 feet apart. Similarly, for a couple of other cases that are available here and one can read about, we're talking about interactions that are more than 3,000 feet apart, things that we just don't anticipate. And I can go on and on, but we won't do that. Okay, and so there's a lot of nuances here. Actually, if somebody is interested, I can provide them a copy of this recent article. It's really quite fascinating to look at the pressure signatures. And as engineers, we always try to remain positive people, that we try and use these fracture hits or as diagnostic tools rather than something being completely negative, because you certainly know how long the fracture is once you see it interacting with the second well. And so here, just, a lot of these things aren't nuances. This is one case that actually occurred. So each one of these spiky regions is a frac stage. So you go in and you pump a stage, and there might be 5 or 6 clusters or less in that stage. Then you come back up the hole and you pump another stage and you pump another stage. And it looked like there were about 15 stages in this well. And you could see a slight amount of interaction between the parent and the child well early on, okay, just due to the formation being pressurized. But ultimately, you can see halfway through here, there was a direct communication in the fractures. There was an interaction in these wells. And one of these wells was going to suffer, okay? You're going to have to downgrade production or go through a lot of remedial work in these second wells. And so I think this is the real message. It's in the Uinta Basin, is that we have situations where the resources are fantastic. So far, horizontal completions have been relatively far apart, but as we move them closer together, we're going to deal with some challenges that we're seeing in other parts of the country in terms of these. In other parts of the country, what people are trying to avoid them in the first place is that they'll be doing pad drilling, or what they're calling tank or cube drilling, where they'll drill multiple wells from the same pad, 6, 8 wells at the same pad. They'll drill those wells, they'll complete them, they'll stimulate them together, and then they'll bring them online together, so that what they do with that is they mitigate the depletion that occurs and the consequent reduction of the in situ stresses that typically attracts wells, fractures from parent to child wells. So what have we got? We've got that method for helping to reduce, helping to minimize it occurring in the first place, to situations for reducing it. And historically, what people have done for reducing it is my all-time favorite is you do nothing, but that's always problematic. You can shut in the passive well, okay? And basically what you're doing in the shut in the passive well is you're hoping you're providing a hydraulic barrier that somehow mitigates fluids from physically moving into that well. And so the people took it one step further after that. They shut in the passive well. And what they were hoping when they shut in the passive well was to allow the pressure to recover to a certain level and a recovery of in situ stresses that would kind of impede fractures growing into that. Temporary abandonment has been tried. It's not a wise idea. Frack and flow. You pump into one well, you flow out of the other well. You just typically can't keep up with it when it happens. Small preloads, where sometimes you're actually injecting into the passive well. And injecting larger volumes as people have found that is effective. They're called defensive stimulations. And sometimes people have even refracked the primary passive well before the stimulation well. So the last slide to just show it together is that this is relevant, and the technology that can be adopted can be remedial technology, and there's going to be a need for remedial technology because, as you can see, our predictive abilities are still lacking. I mean, we see some wells that don't interact at 500 feet. We see some wells that don't interact at 250 feet. We see some wells that interact at a couple of thousand feet, largely because of our uncertainty of scenarios in the reservoir. However, if what we're seeing and people are adopting fairly widespread adoption is this tank or cube protocol where people are drilling all of their wells at the same time. They're cementing them and completing them and stimulating them at the same time, and they're fracking them with zipper fracks, where they're alternating fractures, moving back from the toe and fracking them all together so that they can start production at the same time. This final slide kind of illustrates, simple economics of how this works in terms of this. And so if we look at the left-hand side, you can see production from a primary well only, and you can see production from two scenarios. Scenario one, where you drill the primary well, you produce it, and 6 months later, you produce the secondary well. And you can see that that production is less than if you drill both wells together and fracture them together. So I think this is some of the movement we're going to see for these wells. And from that, we can see with intelligent well design and possibly with these tank or cube protocols that we're going to see higher production combined from these wells. We'll see a faster depletion of the reservoir, which is ultimately our goal. People don't always realize this. A successful hydraulic fracturing campaign depletes a reservoir more rapidly. The problem that we have is that we're depleting a relatively small area with many of these low permeability wells. And so bottom line is there's a tremendous resource. There's opportunities for horizontal and new completions. There's still opportunities for vertical wells, mind you, in certain parts of the basin. And there is room for caution and intelligent engineering to optimize the production that we get from these wells in the basin. Thank you.
Wow.
Sorry.
Thank you. There's a lot of questions, I would think. Which side do we want to, Rich, do you want to start?
Sure, I apologize, I came in late and it's my loss. That was very interesting. I wish I'd heard the beginning. Just two questions from me. You'd mentioned that the well interactions have been noted up to 3,000 feet, basically horizontally. On the vertical, you mentioned 100 feet. How about, is there a maximum number that you've seen in the literature for vertical interactions?
There have been some cases in the Permian where people have seen microseismic signals 1,000 feet above where they were stimulating. Now, once you start to see heights like this, you start to wonder about, are there secondary causes such as poor cement jobs, movement of fluid up annuli and things like this. But legitimately, if you have a fault or some sort of communication, there's no reason that you can't have significant vertical communication. That, and that being said, that energetically, hydraulic fractures prefer to move upwards because the stresses are always less as you go upwards. And so upward growth will be favored unless there are geologic stress conditions that inhibit that growth.
Second question, within that overpressure zone that you highlighted, historically in other basins, other regions that have seen a lot of production over the years, how many decades does it take of production to reduce those overpressure conditions, so you're moving into more of a hydrostatic regime?
Well, I think that it can be a matter of years, substantial years, but the situation here is that in many of these formations that we're talking about, the native permeability is relatively low, okay? And so the native permeability is low. That means fundamentally the regime around your stimulated domain that has been depleted is relatively small. So that suggests that there still remain many opportunities for infills to be drilled in virgin reservoir pressure conditions, so that you are depleting and reducing the pressure relatively rapidly in a very localized region around individual wells. But opportunities for infills remain significant because the permeability is so low that your depletion doesn't move that far out into the reservoir.
Yeah, that makes sense. Thanks.
I'm just testing my understanding. So what you're saying, to maximize production from, let's say, a cube, either a mile long or 2 miles long, you want to drill multiple wells at the same time? Is that what I'm hearing?
That tends to be the direction that the industry is going at the present time.
Rather than drilling one well in a formation and seeing what goes on, to try and drill multiple wells in the formation at the same time to take advantage of the interaction between the different wells. Is that what I'm hearing?
To mitigate the interaction
To
between.
mitigate, okay.
So for the first well, as I said, you drill the first well, and as you deplete the pressure, even locally around that well, that will act to attract the hydraulic fractures from the second well. And those hydraulic fractures, they're not mathematically symmetric entities, although that's the way we treat them in models, is that if one wing of that fracture is attracted here, you may not grow a second wing. And so you may be covering a smaller drainage radius with the second fracture even than the first, than what you'd anticipated. So I think you drill them together to mitigate the interaction between the wells, or minimize.
On the right here, Gordon, or Mike?
So I've heard cube development. Where does tank come from?
I think that they're synonymous.
Okay.
That basically you're exploiting a tank or a cube.
And you did use an important word in your presentation there. I did hear regulation one time there.
Against my better judgment.
Yeah. And I can't remember exactly what the context was, but we're pretty early in the Uinta Basin as far as, we are seeing 1 or 2 wells, sometimes 3 in a drilling unit, different zones being tested. At what point would we have enough information to even want to try to suggest, because the operators, they're the ones investing millions of dollars. They don't want those wasted by any means. What can we do to help the process, and at what point do we even, what have you seen in other states where regulators have gotten into trouble by getting in too soon or not doing enough, doing it too late? And I can't say what regulators necessarily done in other states. I always advocate education ahead of regulation, that it works better for everybody, that empowering these operators to know what is done in other scenarios, and most of them are very familiar with it, is much more fruitful than prescriptive measures. Good, thank you.
And I think if I could add to that, we have such a difficulty in predicting what goes on now, largely because we don't necessarily comprehend the complexities of the reservoirs, the fractures that exist in the reservoirs and things like that.
So that was precisely my question. This information was wonderful and new for most of the board members. How prevalent is this knowledge with our operators, and how far apart are they? I mean, how do we educate operators so that they're all, I mean, most of the time this stuff is confidential, is classified information, could be considered a trick of the trade or something confidential. How do we get this information disseminated so even the smallest of operators are using these techniques the right way?
Well, this information is really no longer confidential in many cases. I mean, the train has left the station. Once it reaches Wall Street, then everybody starts to, many companies start to become aware of it. And what's happening is that investors have been looking at parent-child relationships and realizing that the sum of the two production is not, the overall production is not equal to the sum of the individual wells. And they're looking at reserves estimates and asking people to cut back on reserves estimates. So there's a lot of pressure that's coming from the financial sector right now. And I think that working through, we'll give Mr. Baza something else to do. I mean, just sort of an educational component is really going to be important in terms of people understanding this. I don't know the specific answer to your question in terms of the best way to disseminate that information.
Yeah, I mean, it just seems to me that it's going to be discovered by a catastrophic conclusion rather than engineering ahead, and just because of the unknowns that Gordon talked about.
Yeah.
So I don't know when we go to issue permits or when we rule as a board if we're even going to have the information available to know if spacing is going to cause a problem, or if their fracking programs are going to cause a problem. It's a difficult challenge to fully utilize this information.
Yeah.
Susan?
Following up on what Mike said, often we see presentations where they talk about ultimate recovery of about 3% from a basin, from an area, a drilling unit, let's say. And then when we look at horizontal, they're projecting 10% ultimate recovery. It looks to me like what we're really looking at is cube production to get the highest estimated ultimate recovery. And we've seen a lot of horizontal drilling, but not what you're recommending, which is simultaneous drilling to mitigate these interactions. We only have 5 drilling rigs in the basin. I mean, how in the world could we even do something like that with only 5 drilling rigs? What's the ultimate recovery we can expect if they did this type of a drilling regime, I guess is my question.
I'm not sure I know the answer to that. And I appreciate the difficulties of applying this to something where you're drilling a small number of wells per year. And so under those circumstances, you may need to be looking at techniques that are defensive tactics rather than the cube drilling, where your prophylactic measures where you're actually pressurizing the existing well or something along those lines. Because you're absolutely right. I mean, the economics of this is favored in production operations such as occur in the Permian. I think your production figures are reasonably accurate from what I've heard, is that 3% for vertical wells, 10% for horizontals for oil, somewhat higher for natural gas. And where do we go from there? Really, the only logical approach is you have to have more fracture stages and closer spaced wells. And if that is going to be the case, then there's going to be a greater propensity for this kind of well interaction happening. And with that, you come with requirements for larger amounts of water and more frac sand.
More questions? I have a few. One of the companies that is going to be involved in Utah is Uinta, and I can't speak for them, but my understanding is they bought Newfield, and then they laid the rig down for 3 months to look at just exactly this. They said, we want to know the science better. And then as we look at Wall Street Journal articles about what they call the production prediction gap of where they correlated the first well and said, well, all the wells are going to be basically this productive. And then they came back, the financial community then was told, wait a minute, you know, we may have overstated this. I think that's kind of what we're seeing. And I think we're in, you know, a new basin. But if you were king for a day, what we're trying to do is prevent waste and to have policies that have the greatest ultimate recovery. So if you were king for a day, knowing only the beginning of what the real problem is in terms of the science, what could we do as a board in terms of trying to say, okay, what is the education that we need before we do the regulatory steps? One of those I'm hearing from you, as at least I understand it, and I'm going to try and feed back what I heard you say, is that the cube development, which is a lot of articles were written on that. The tank development, I think, was Questar QEP came out with a tank development discussion. But in any respect, they're coming in with the idea of drilling multiple formations at dense drilling. You had a slide that you mentioned, the lower left-hand side of it. What would be the smart poker? Like, yeah, if you could go back, there's one slide that had 4 panels, this one. And if you look at, this is the one that just intrigued me the most. And I'm going to invite you to maybe talk about this more for just a minute, if I could. Tell us more about what this slide means, and particularly the lower 2 panels.
Okay, so we can look at, I mean, the lower two panels characterize on the left the Midland Basin, and on the right the Delaware Basin, and formations that are present. And so, historically, in the Midland Basin, for 75, 80 years, we've been drilling wells in the Midland Basin that were vertical. And those vertical wells would intersect some of the formations that are shown here. You know, going from the Middle Spraberry, I can't read all of these, through the Wolfcamp, through the Mississippian, the Dean, various formations. And we were fracturing vertical wells, you know, much like what Anadarko does for their gas properties. You've got different zones at substantially different depths and fracturing them. And we moved into situations in the last 15 years where we've recognized that formations such as the Wolfcamp that are shaly and low permeability formations like the Spraberry can be accessed by horizontal completions. So we moved towards drilling horizontal wells. I think some of the first horizontal wells in the late 80s were drilled in the Spraberry by Shell, for example. And then as time has moved on, we've recognized, as Ms. Davis pointed out, that the EURs are very low. And so how do you get around those EURs? Well, the one method is bigger treatments, bigger frac treatments, or more wells being drilled in greater proximity. And so what you can see is moving from 1 or 2 wells per section to, as we can see here, I mean, these are six or 8 wells per section drilled from a single pad. In general. So not only is your footprint reduced, but your reservoir coverage is increased. And so the decisions are made by these organizations in terms of how closely they're going to space their wells. And that's based on technical insights from, as you've mentioned, I mean, there have been disasters that have happened. I mean, they basically have had experiential evidence that this is how close they want to put their wells together, and this is how big the treatment they want to do. Now, some other operators believe that you can get increased coverage by putting in more wells, and they use sort of the Chevron type arrangement where you can see that they're putting in wells at different levels. And this particularly makes sense in formations that are thicker. That the biggest question that we often have from a geologic perspective is, where do you land your horizontal well? What zone do you put that in? And how much vertical frac growth are you going to have, and how much interaction you're going to have in that frac growth? So you can see in the lower left, in the middle Sprayberry, Pier 1 and Pier 3 believe that they can use a Chevron relationship, and they can take advantage of the fact, and they're taking advantage of the fact that they believe that these multiple wells are each going to drain discrete individual areas that are not interfering. Now, whether that's true or not remains to be a significant question, and that's that question that people are debating. And you can see it becomes even more substantial when you move down into the Wolfcamp B. I thought it was the D, but it's the B. Okay, the Wolfcamp D on the lower left, where you can see some of these folks are drilling wells that are very, very close together. Now, the rationale for drilling these wells very, very close together is that the proximity of the wells is a direct function of the reduced permeability in the Wolfcamp as opposed to the Sprayberry. So an individual is going to look at the reservoir engineering that they undertake, and they're going to make some sort of decision in how close they can put these wells together without substantial amount of interference. And I think the jury's still out in terms of how much interference we're really going to get for these wells, and whether or not people will back off in these aggressive treatment designs. We see it happening, closer to home. We see this happening in the Basin, as I mentioned, where people are looking at they're drilling cube drilling in the Three Forks and cube drilling in the Middle Basin, and trying to stimulate those sequentially, or all together, but sequentially.
That leads me then to the next question is, because the knowledge base is imperfect and basically immature at this point to some extent, what questions should this board be asking as the operators come before us to get our authority for whatever they need that we control? Because what I'm getting out of this slide, let me just kind of get to the lowest common denominator. You have Pier 1, 0, 1, 2, and 3. And one of the things that we're going to be looking at is a rule on operatorship, where you may have 2 operators come in. Let's say, for example, you had Pier in the lower left hand, you had Pier 0, informed. They're not novices. And then you have Pier 1. So it would be Pier 0, Pier 1, and they come in and say, each of us wants to be operators. You choose between us. Clearly they have, as to the middle Sprayberry and the next formation down lower Sprayberry, you can see that they clearly have different philosophies. Mm-hmm. And different understandings. like I said, in Canada, I mean, I'm not speaking for them, but my understanding is they just said, we're not gonna release the rig, we're just gonna lay it down. We're gonna try and get a better understanding of the science behind these wells. And then we're going to develop a program that is much more information-based and start working through the problem. The operators are going to keep a lot of their information proprietary, but what questions should we be asking concerning this? So you have parent-child, you have wine rack versus stacked, you have best frac techniques that are recommended. Have the scientists, and the next question would be, have the scientists pretty well agreed as to the technique that ought to be used? What can like the Utah Petroleum Association, what questions should they be asking that they can come and bring to us to educate us? Because we're making some very important decisions here. And let me give you that in context, and for those that are watching on YouTube, we are in a pilot project. We took a course different from a lot of other states, where our beginning drilling, rather than having a firm regulatory base that didn't match the science and didn't match the information, we took a pilot project approach so that our rules and orders have a sunset after 5 years. And so we're now getting to the point where some of these are coming to sunset. And one course would be to say, we were right, just extend the order, or is more importantly, is there anything we need to add to those that would encourage a direction toward frequency and proximity of wells, that would incorporate lessons learned? What else could we do, I guess, is to bring up the regulatory educational level of both the division. We have petroleum engineers with a division. Are you finding that they need to have some secondary kind of best practices conferences or something like that we ought to be encouraging them to be involved with? I've never asked a more complicated, multifaceted question, so I don't know how
Thank
you're
you.
gonna, but I am done with that question. Thank you.
Well, first of all, I think education is always prudent, and the more opportunities the staff have to be familiar with what's going on in other jurisdictions, the better off everybody is going to be. Secondly, I think that it's always prudent with these applications to sort of, well, I don't like to use the term reward, but to favor people that are going to do measurements in science and monitoring that can establish science. And I think there's a lot of opportunities for infill drilling with monitoring in some of these other wells that, in fact, there may be intersection in these wells, but they'll be, it will be established. And so there may be some wells that are on decline that need to be reworked that could be used as monitoring wells. A lot of the information that's being gained in the Permian has been, and it's big money, and it's not necessarily applicable to this basin, has been multi-company drills where they've drilled and they've fracked and they've monitored. I think that you can do this on a scaled back program to maybe do some of that. I think that well, it's prudent to have regulations with the sunset. I think it's very prudent to have regulations with the sunset to be able to revisit them. I think proceeding conservatively is always the best, and you can modify those rules sooner rather than later as information comes in. Because I think the jury is still out in terms of many of these things, in terms of everything that you talked about. I mean, you know, the stacked, the wine rack, the spacing. Many of these things are governed by geologic anomalies, natural fractures that we don't have seismic data that is necessarily going to show that. And so we want to encourage people to participate, yet be cognizant of their neighbors and aggressive notification, as is commonly the case in most of these jurisdictions. And Mr. Gill, I'm not sure I know how to answer your question.
I didn't know how to ask it. So, you know, one of the decisions that operators can make is the orifice size and how fast to produce these wells. You can produce them very fast for economic reasons, or you can produce them very slowly to learn more about what they're doing. Is there anything in that arena that is, I'm very reluctant to get into the science that the companies use, because there's no way that we as a board are going to be able to have the full base of knowledge that they would have. But do you want to encourage faster production to reduce some of these stresses? Do you want to slow it down for more study? What do you suggest in that arena?
So one of the things that I've read, and it makes sense, is that most of the observations of interferences have been when the reservoir pressure has been reduced substantially. And so you start to see these things happening after IP and after early production. And I think that you really have to allow people to produce as aggressively as they want in early times in order to be able to have favorable economics in these plays, because it depends on additional drilling, and additional drilling is contingent on accelerated production. So I think it's an economic question.
I'm willing to go half the day if there's still questions. Go ahead, Gordon. We're over time, but I think this is one of the best discussions we've had in a long time, and so would like to keep this going for just a few minutes, and ask for those that are here to give us for going over time, but let's keep going on this if we could.
Are there some common practices that maybe we could encourage? Because if one company's drilling, they're going to want to monitor all this. The concern being when there's a neighbor, and they're going to need to work together, but whether they will, or maybe talk about that, and then what types of monitoring can we invite? I mean, I'm not for regulation, but so that we are learning as much as we can and encouraging that common working together.
Yeah, I think underground trespass is. I was an expert witness one time in an underground trespass case, and I think we're going to start to see more of that with these things that are going on. Just in terms of fractures intersecting wells across lease lines and things like this. And so I think that these things are very, very difficult to avoid, notification and conversations up front is about the extent that you can do, and it's to everybody's benefit, of course. But the smaller operator may have a harder time taking measures to protect their well, because they're losing production in terms of taking measures to produce to protect their well. And if you start to make setbacks too large, it just works against you. I mean, so some of this is going to happen.
All we need is the wisdom of Solomon, and we'll be just fine.
X-ray vision.
With X-ray vision of Superman. Any more questions? Yeah.
This is for John. John, can we get a copy of this presentation, or Dr. McClellan? Is this something you'd be willing to share with us, or?
I normally go by John. I prefer
Well, I was
that.
looking at John Baza and Dr. McClellan, so I was trying to,
Of course. Yeah,
thank you.
of
If
course.
And I
Mr.
do have his presentation, a copy
I
of it.
I would love to have a copy.
We'll
I
get
think
that
Could
it's
it maybe
excellent.
be linked to our agenda today, would that be possible, so that we can?
I'm fine with it, but I know that John borrowed a lot of his material
Yeah.
from one of our geologists in UGS, so we'll make sure we have permission to do that.
Okay, thank you very much. Thank you. Well, with that, we are over time. Thank you, Dr. McClellan. John, back to you, John Baza.
Okay. Well, thank you very much. Just one thing that I wanted to talk about, which is pretty critical because it's coming up in June. And we had intended on having a June field trip and board hearing to the Price area. But as we discussed it as a management team and amongst our staff, there were some difficulties. One difficulty is that we had a matter on the agenda today that now is going to get continued to June, which affects one of the properties in the Price area we were actually going to go look at. So with that in mind, I think that we had decided as a staff, and we ask your indulgence as a board, if we could postpone that Price hearing and field trip until later in the year, which means we would just go ahead and have our June board hearing here in Salt Lake and do away with the field trip the day before, putting that off until probably September or October, if that would be meet your
I think
approval.
we would encourage that.
Very well. So we will go ahead and plan our Salt Lake City meeting in June as we've discussed, and we'll just see you again in June. Other than that, I know we have the Governor's Energy Summit next week. Quite a few of us from the division be attending that. We've got some board members registered, so we'll look forward to doing that next Thursday. Thank you very much.
Thank
sir.
you very much. With that, we'll take a break till about 10:30 and come back. That'll give everyone time to know when we're going to go back into session. With that, we're on a break.
That was great.
I wasn't expecting questions.
It's kind of like your students, you know?
Yeah, no, these are tough students.
But it was one of the most fascinating, and I expected it to be one of the most fascinating discussions. It's interesting.
Hi.